Thanks, Ralph. So we thank everyone for attending this presentation today. We hope you find the information informative and useful. We're going to discuss investigation testing of existing structures and construction materials. We're going to touch on the investigative and testing techniques for evaluating existing structures and construction materials. We're going to review those techniques and equipment used to evaluate various materials such as concrete, steel, masonry, stone, and wood. We'll discuss the advantages and limitations of each test method and outline the general principles and reference standards for each test method. Below is a list of references that may be helpful. Several ASTM and ASCE documents, guides for property condition assessments, guides for structural condition assessments, guide for construction assessment of building envelope, and then ACI has a concrete specific guide, which is repair, rehabilitation of existing concrete structures. There's also an ASCE publication that was authored by Joshua Carden, which is the guidelines for the forensic engineering practice. There's also the Forensic Structural Engineering Handbook that is useful for forensic structural engineering. Below is a table of a variety of evaluation NDE methods that we've categorized them as basic, intermediate, and advanced. We'll start by talking through the basic, proceed to intermediate and more advanced. A few of these, although they're considered non-destructive, they do involve some limited, localized, you might say, damage to the area in order to perform the evaluation, such as a screwdriver test, the plug tester, and potentially load testing. So it's important to have the right expertise with the equipment in the background and the structure. It's important to have a knowledge of general and advanced theory of these various techniques so that you know the capabilities and limitations of each technique you're using. And it's also important because they're somewhat subjective or qualitative in some instances, it's important to verify and calibrate the results. As I mentioned, it's important to understand the type of construction that you're evaluating and the materials that you're evaluating, and the potential failure mechanisms of the various structures and material, be it mechanical or chemical. And then it's important to have the ability to assess the significance of each of those. The most common NDE technique, which often is not thought of as NDE, but it's a visual survey. So there are various forms of completing visual surveys of structures, and a lot of it does depend on the access to the structure. So it may involve, if it's a tall building, suspended scaffolding, it may involve pipe scaffolding, aerial lifts, or rope access is another option. If those are not available and the structure is relatively far away, there is the opportunity to use, say, binoculars and telephoto lenses to evaluate a structure from a distance. There are obviously limitations to that. It's much better to be up close and hands-on to do visual surveying. As you can see here, one of the projects that we had worked on, we had used industrial rope access to evaluate the Washington Monument after a seismic event, where our difficult access team was able to rappel down the monument and look for deteriorated, damaged, more so mortar joints, and stone. Another fairly useful technique is sounding. It can be used for concrete, stone, masonry, and usually involves hammer tapping for floors, vertical and overhead surfaces. You can also use what's called a chain drag evaluation, where you have a chain and you drag a metal steel chain on a surface, and you can listen for changes in the sound of the material you're sounding, and with the goal of identifying areas of delaminations in those surfaces. Also available are more proprietary rotary percussion tools, which have extension poles that are available for areas of walls up higher or overhead. Basically listen for the same type of changes in sound. So obviously there could be issues. One of the cons with listening is if there's a lot of background noise, it can be hard to decipher. Worked on one project where we're doing hammer tapping and there was jackhammering nearby. So in an instance like that, it can be a little challenging, or other types of background noise when you're listening. Another sort of basic NDE technique is evaluating concrete with devices such as a Schmidt hammer or a Windsor probe. Essentially, a Schmidt hammer is a handheld device that imparts an impact on the surface, and it gives you, I would say, relative strengths. So that doesn't give you an exact value for compressive strength. However, what we often typically do is calibrate the Schmidt hammer or the Windsor probe by taking cores of the concrete and then breaking the concrete in a lab to try to correlate. So this can be helpful if you have a large area of concrete you're trying to evaluate, and you're trying to determine if there are certain areas that may have a lower compressive strength than others. And then the Windsor probe actually involves powder cartridges and a little steel probe that you can see in the image in the lower right. It basically embeds with a known volume of powder the steel into the concrete, and then you can measure the embedment, and that can be somewhat correlated to the compressive strength, albeit sort of near surface concrete. Another commonly used technique is metal detectors. It can be used for stone, masonry, concrete. One very common manufacturer is a Fisher meter. You can see in the photo here, it's being used on a facade to locate anchors for the facade panels. So you can identify the location and the quantity. It's without having to, cut in to the facade. So it's relatively inexpensive and easy to use. It gives off an audible signal when you're near a ferrous material. Now, one of the drawbacks, of course, is that it doesn't penetrate very deep, typically less than 4 inches, but it can be useful for near surface steel. So another fairly inexpensive tool is the screwdriver. So in this case, the screwdriver test is being used to evaluate individual wires in strand, PT strands. There is some limited, as I mentioned earlier, localized destruction as you're creating the opening in order to expose the PT strand. You remove the sheathing and you expose the wires. So the idea here is you attempt to wedge a flathead screwdriver into the wires, and you get quite a bit of resistance, as you might imagine, if that strand is stressed. However, the wires tend to loosen up if the strand is relaxed. So it's a sort of quick, low-tech way to determine if the PT strand is tensioned or detensioned. One of the potential complications with this test is if the strand is detensioned and it is somewhat wedged along the sheathing in some other locations or partially detentions, it may not be entirely conclusive. One test used for wood materials is the screwdriver or the screw withdrawal test. So in this instance, a screw is driven into wood, particularly fire retardant treated wood, and then a pull tester is used. You grab on to the head of the fastener, and you essentially pull on that test to check for brittleness and quality of that wood. Another NDE technique used for wood is moisture meters. There are various types and kinds of moisture meters. One shown here is manufactured by Delmhorst. It's a fairly common handheld device that can be used to check the moisture content of wood fairly quickly once it's exposed. It can also be used for gypsum, wallboard, eaves, bat insulation, and on occasion we've used it for concrete. So that you could get a wide range of results. So one of the drawbacks is that it could, depending on how you insert the probes and how they contact, you could get a variation in results. If you were really looking to confirm the moisture content, you would want to get a sample and then have, the moisture content of that sample tested to verify. Another fairly common device used for evaluating wood is resistance drilling. One of the devices is a resistograph, and what it does is you essentially drive a drill bit into a wood member, and depending on the amount of resistance in that wood, you can tell whether there may be the presence of decay. Obviously, if it's decayed, you're not going to have much resistance. However, if the wood is sound, you're going to have a higher resistance. However, this device, you want to do sort of multiple tests. It's highly dependent on the drilling direction relative to the wood grain orientation. So those need to be considered. Now, getting into steel, you may be familiar with magnetic particle testing. It's often used to look at the conditions of welds, to inspect the welds. Iron filings are placed on the surface, and then this device is applied to the surface, and the iron filings are sort of drawn to sort of deficiencies and cracks, and it can detect those. And the ASTM, there's a standard for this method. You can see in the bottom right corner, it's being evaluated at the base of a pole at the intersection of a pole and a base plate. Another similar concept to evaluating weld is the dye penetrant or liquid penetrant evaluation, also used for weld inspection. The surface is prepared prior to application of the liquid dye. And one of the drawbacks to this method is there is somewhat of an extended dwell time. You're not going to have sort of an instant result. And then another drawback would be there's potential strong odor. If you're in a confined space, you need to take that into consideration as well. And then, as I mentioned, the preparation is pretty critical to this method working. And these photos show some potential issues with the weld following the application and removal of the dye. It sort of stays with the deficiency of the weld.
Jason, that project, there were actually billboards. There was actually a town where a billboard fell, and we were looking at the weld quality, and that, unfortunately, lots of issues with welds on those particular signs. So that's kind of interesting too, and that's what those pictures are from. Just very poor fusion in those welds.
Gotcha. Thanks, Ralf. So next we'll talk about geophysical and electromagnetic methods. These include eddy current, which we talked about briefly with the Fisher meter, radiography, X-ray, ground penetrating radar, GPR, and infrared or IR thermography. So I'll hand this over to Ralf after I discuss this one. Is eddy current. Similar to the Fisher meter, there are several devices that provide a little bit more information using this technology. With the Fisher meter, you can't really determine depth. You can determine the presence of steel. With the Prosec, Alcometer, James R, and Hilti meters, you can get an approximate depth of magnetic field penetration. In this case, we're looking for concrete cover, measurements. With this method, obviously, you can get approximate measurement. However, we often recommend doing exploratory openings or drilling at location of rebar to verify sort of the readings that we're getting. So these devices can be used to determine the location and spacing. They also can estimate diameter, although a lot of that does depend on the calibration. So it's pretty important that that gets calibrated, because you can tune the machine into identifying changes in rebar diameter.
Right, thanks, Jason.
Sure.
Hopefully that works and everybody can see my screen. I'm going to be talking more about some of the intermediate type of NDE techniques, and one of those being X-rays. This is a pretty old technology, as probably some of you know, and it does have kind of a unique application. In this case, this is actually a project where we were looking at post-tensioning, and there was actually and I'll use my pointer here. There was actually a construction joint right in here. And what we were trying to do, there was some post-tensioning tendon failures in this building, and we were trying to, and somebody's got their mic on. If you could turn it off, that'd be great. But we were actually trying to determine on which side these were intermediate stressing anchors and post-tensioning, and we were trying to figure out on which side those anchors were on, because it sure did matter when we were trying to detension some of these cables and repair them. So in the bottom image here, in this green, you can actually see the anchors. So that's kind of one of the benefits with X-ray, is that you can actually get a physical image. Unfortunately, there's no way to tell depth. It won't tell you, as far as rebar and things like that, how far down they are. But it does, like in congested areas, it does kind of give you a real image. Both sides of the structure have to be available. The other parts are that, you just really have to close off the area to the public. It's kind of like getting an X-ray done at your doctor's office. You got to protect the public. The other part is the exposure times. It really depends on the thickness of the material of the concrete. And, just for example, it takes about 30 to 45 minutes just to do an 8-inch thick slab, just to get enough penetration through there to actually get a physical image. So now getting into more of the GPR, ground penetrating radar type equipment, there are various antennas. Some of the units actually can use different size antennas. With the lower frequency antennas, you can actually go deeper, but the resolution really kind of dissipates. So for those, these kind of 100 megahertz antennas type systems, you're kind of really looking at like really doing soil, locating utilities and that kind of thing. Whereas some of our forensic work that we get into, just looking at concrete and trying to locate reinforcing and things, we're actually looking in the 1.6 gigahertz to 2.6 gigahertz, and you can kind of see the differences in potential penetration of that signal. And again, the deeper you go, you kind of give up on resolution on the images. Kind of to the right here, you can kind of see the images. This would be typically the top surface, and these little peaks basically indicate that there's an embedded reinforcing material there. As I said, there are different types of units. They are sensitive to metal embedments and can certainly help you locate things pretty quickly. The other thing that's nice about it is you can actually record these images and you can replay them, which is helpful. And the graphics are super helpful as like presentations. If you need somebody to actually physically see some of these things of what's been found in the field. The kind of the negatives on this is that, and a lot of the NDE equipment, you run into this issue, is that if you have a congested area, it can mask some other potential, if you had a bar right underneath here, it may not be visible. You may not be able to tell if there's 1 or 2 bars, if they're stacked. So if you have really congested concrete areas, you may not be able to find everything with the GPR equipment. You're actually shadowing some of these things. You also can tell the rebar size, and as Jason kind of alluded to, we always verify. So part of the work would certainly involve doing some openings or drilling some holes to verify maybe the rebar sizes. So that's kind of important. The other thing that can happen is, it is difficult to work with this equipment if it's wet, and it actually does impact some of your readings as well. As far as it does actually have a vertical scale that will give you cover, like the depth to the top of the bar, for instance. And so you kind of have to figure out, what's the proper constant to use for that and the GPR equipment. That's why it's kind of an intermediate type system too, is you really need to understand it. It's not just a black box. So not every concrete potentially is going to give you the same kind of thing. If you're really looking at detailed cover measurements, you really need to calibrate this equipment. It also can help you locate cracks or delaminations or honeycombing or anything like that, voids basically in the concrete. And we discussed this already as far as just resolution decreasing as you go to lower frequencies. Here's an example of just an image of, just a masonry wall, which is really kind of nice, that you can scan and you can actually find, you can see here the CMU block, you can actually see the vertical, the web, or you can see actually grouted cells or non-grouted cells with these scans. Combining this with we'll talk about later about IR, the infrared, you can really figure out what's grouted and where the rebar might be in a wall pretty quickly. This technique is also NDE, but it's basically half cell or corrosion potential. So basically using a voltmeter, this is for concrete, and a copper sulfate half cell. And it's basically you creating a circuit. This is kind of gives you an idea that kind of one of the downsides is that you actually do have to connect to the embedded rebar. So you do have to do a little bit of an opening, and you're assuming that your rebar, your cage basically is in contact, bars crossing or in contact with via tie wires and whatnot to complete the circuit. So you're measuring the corrosion potential or risk of corrosion is the purpose of this kind of testing. And you kind of create it, you can kind of, with some of the data available, the databases available now, you can actually get a almost like a topograph of the corrosion potential. So when you're down like below negative 200 millivolts, they're really, I mean, higher than that, since we're negative values. If you're going toward the 50 and up, there's no not real corrosion potential, but it increases as you go kind of down, even lower values. So when you get into the 500s and so forth, so you can kind of see, this particular graph, the red obviously meaning that there's a higher corrosion potential in this area. And the reason you would do this is if there've been issues on a structure and you're trying to figure out, as far as service life, the potential for delaminations, that kind of thing, you could do an assessment. Moisture is important. It can impact some of the readings, because you are basically creating a circuit, completing a circuit, as you can see. So you have this sponge that's actually with moisture attached. So you're trying to basically read the current, the flow of current through here. One of the things too, in the past, we've run into, like, if you're, we've been in like industrial facilities and things like that, there may be chemicals that can also impact how conductive the concrete is and may impact your readings. So those are just some things to think about. Kind of spoke about IR, infrared thermography. It's pretty common, but there's a lot of mistakes too that can be made using this equipment. It can be basically used for masonry, for concrete work, for FRP. So fiber reinforced polymers, like reinforcing, we've used it for that. There are a variety of cameras available. You could get some, obviously, at like Home Depot, little handheld units. It basically measures the emitted radiation at the surface of the whatever element you're looking at. So it's near surface defects that you're really looking at. And sometimes, we're seeing things where people are reading more into it, where you're actually looking at moisture in walls and you're looking at the surface, and it may be heating from just the sun or reflections off of windows, adjacent windows and things. So there is some training really required, or knowledge required, to use these. They do give you great information, but you've got to be careful. You are reading kind of the surface. You're not reading anything really behind it. So if you have like a stud wall and gypsum, that may not be indicative of the wood framing. And it can be used to basically find actually voids. This is actually a bridge deck. It actually can be, used to find actually voids in concrete potentially. The thing you have to be careful of is when you do these types of readings, temperatures and things like that. As far as the heating of this, usually we try to do this work at sunset or sunrise. So you have kind of a limited window because the surface, obviously the solar heating. And then for FRP, basically for wraps and things like that, we've used like lamps actually just to briefly heat the surface, and then you can get instant readings to try to see if it's delaminated or not. One thing to keep in mind is, the cameras also matter. And I mean, there's various ones, they have various temperature readings, sensitivity. They also have different pixel resolution. The thermal image is actually stored within those pixels. So if you've got a coarser image, you may not get the temperature gradient or even find a defect potentially and miss something. So it's something to keep in mind. This is kind of an example. This is a project we worked on a high-rise building that had concrete block with directly applied stucco on it. And you can kind of see the darker areas. Those are actually grouted cells. And you can kind of see here the discontinuities, right? You can see that some of the window jambs, the window jambs aren't grouted. You can kind of see they stop and start. And these are supposed to be reinforced mason, CMU walls to resist potential high winds on the coast. And so that was obviously an issue, but this was actually done. I did these scans, in the evening, and some of these in the mornings. It can give you some pretty rapid information as far as some of these potential deficiencies, as far as lack of reinforcing or lack of grouted wall areas. Just kind of going into this is, basically you have the heat flow, and you kind of, with the camera, it picks up that heat flow. And then if there's a discontinuity, basically you have cooler zones, and that's basically what it's picking up on. And it is also used for roofing. It's pretty useful for that. This is something, that this is maybe not the latest camera. There are some other ones out there, GoPro and Instacam. These are just 3D imaging and video survey tools that are fairly inexpensive and pretty useful to document things very quickly. It basically allows you to kind of conduct a 3D walkthrough potentially with a client or anybody. You basically record it. It's basically has a lens on both sides, and it does a 360, kind of like the realtor's tour of a home, which is kind of nice. And this is actually one that we build out of an RC car to, kind of get into areas that may not be safe potentially to access, or to determine if it's safe to access certain areas. So we kind of use that actually to enter the areas and get video images and so forth. And basically you can view the images live off of a, tablet. So it's kind of nice. One of the disadvantages is that some of the software, and one of them is sort of Matterport that's out there. It's a nice package, but you actually have to pay a monthly service. They kind of process the images for you, but you have to use kind of their service to actually view them. So it's kind of a little bit of a disadvantage for that. But there are other vehicles to use for this. We can actually use this in combination with drone footage and things, where we can actually mate these together. And we actually can do 3D imaging and fly-throughs, virtually. Basically you take those images and you can just go in and we actually use it to do quantity takeoffs potentially. You can, look at concrete spalls and such on the images, and you can map them out and then use the software to actually get quantities. So here's just a little thing, like just a taste of like the Matterport software, what it does. And this is kind of the output I was able to copy. And unfortunately, if you go to their website, you can actually walk through. This kind of shows you, you set up certain points with the camera and it creates this 3D image, and you can kind of go in and out of it and walk around and zoom in and out of different areas, which is kind of cool. So now I'm going to get into more advanced, potentially NDE techniques that are more ultrasonics related, and part of that is the through transmission ultrasonics, ultrasonic pulse velocity, and cross-hole sonic logging. You can kind of see, schematically here, you basically have to have access to both sides, to both sides of like a slab, a column, or whatnot. That may be a disadvantage. And I'm going to go into more detail about each of these. Then you have the reflective ultrasonics, which is basically ultrasonic echo and impact echo. You're basically impacting, and then you get a signal that you read. You can do from one side. The other one is tomography, or ultrasonic shear wave tomography. It's a newer technology where you have multiple impactors underneath this thing, and it basically creates a 3D image. And then we have also impulse response. So let me go through a couple of these here. The UPV can be used for concrete and wood. We probably use it more so for concrete. And as you can see over here, this is actually looking at fire damage. It's super useful for that. And basically what you're looking at is trying to determine differences in strength potentially. So you can identify low strength concrete and wood areas because it's the way the signal travels through the particular medium. You can identify voids and delaminations in concrete. You can also evaluate crack repairs, so whether they have been fully epoxied potentially, something you're injecting and you're trying to figure out if it's been fully filled. You can also, with some correlation work, determine like elastic properties such as the modulus, compressive strength. That can be done, and obviously you need a more advanced user. And again, like I said, both sides have to be accessible to do this. So some applications, this may not be the right technology. The cross-hole sonic logging is really more for concrete piles, and you're actually having to core two parallel core holes, which is obviously can be very difficult. But you're basically sending a signal across, and you're looking at trying to identify defects in these piles, and basically voids, or maybe where the shaft collapsed and you've got soil fill in there, whatnot. So the disadvantages is the coring and potentially having to go fairly deep to do this. And there is an ASTM standard here that I'll list as far as just for reference if you're interested. And then now I'm going to get into the ultrasonics, that I used in ferrous and non-ferrous metals. Those examples would be pins, eye bowls, anchor bowls, headed stud, embedded plates, and like groove welds, those kind of things. You can kind of see the different probes or transducers that I used. So you need a signal generator, a transducer, which is this, and then a couplant, which is typically, a gel material, a contact area. The pros of using this is that you can get, the easy ones are the thickness measurements. We use it a lot to find thicknesses of steel members, especially when you look at corrosion, cleaning the surface off and trying to figure out the loss of steel cross section. That's very useful for that. Highly accurate at detecting flaws. Basically, if you have like pins or rivets or anchor bolts or whatnot, and you're concerned that maybe they're fractured, you can actually determine if they are fractured with this NDE type technique. Single site access is used, so that's super helpful too. Now, one of the potential cons or problems with it is the surfaces matter. If you don't have a good surface to work off of, you're going to get incorrect data. So they're pretty sensitive to that. So if you have corrosion, a corroded surface, you may not be able to transfer the signal. You may get erroneous readings. And there's pretty significant interpretation required with this type of equipment. It's not a novice kind of thing where you can just pick it up and use it. So just keep that in mind. Other than the thickness readings, some of the instruments here, this is like, it's pretty basic. It is fairly easy, but some of the more advanced type of testing where you're looking for fractures and things like that, you really need an expert person to use it. One of the things that's kind of also a negative is that you have to document the locations yourself. They're not automatically recorded with the equipment, so that could be an issue on some projects. And then you have to use a reference standard. So anytime you're doing this testing, you're kind of going back and forth sometimes to recalibrate your equipment. So there's like standard thickness plates and stuff. You have to basically calibrate your probe or transducer. So that's kind of time consuming. I wanted to show you this example. This was actually a project I worked on where we got a call on, it's a parking deck that had precast panels that were supposed to be attached to these columns. And there was concern, apparently, that when the rebar was placed, some of the ties were in the way of the plate, and somebody decided to bend the studs. And obviously that impacts the capacity of those embed plates and the stud orientation. So we're actually able to use the UT to determine the approximate range of angles of the angle of the headed stud. So that was kind of interesting to do non-destructively, and we verified that. But that was a neat way to use this equipment as well. Shear wave, again, this is the equipment. It's typically the mirror is the one out there. It's used for concrete, grouting tendon ducts, 3D images. You need single access. Expert user for sure would be needed for this. But what you're looking for is actually voids, like in a duct, in a pre-stressing or post-tension application, where you have ducts that are grouted. So here's kind of an example. This is actually the mirror right here, got like a handle on each side. And then this is like a duct with voids in it. And you can kind of see the images, the red kind of indicating that there are voids in these various locations. Impact echo is, kind of a technique. You're just using an impactor, as you see here, and you're introducing an impact, and then it basically reflects off of potentially a void. And so it is finding cracks, voids, delaminations, that kind of thing. You can determine thicknesses. Again, it really does require expert experience, because this is like the impactor, and there are various size impactors that can be used. And it's kind of a trial and error kind of thing, or experience level as to which kind you need for certain applications. Impulse response is somewhat similar. It's just a larger impactor. You can take rapid readings. The problem with it potentially is that it's not as accurate. but you can detect voids underneath slabs with this type of setup. And again, expert user would be recommended for this. This is kind of one that we use quite a bit too, is the pluck tester. It basically is used for post-tensioning. That's actually a post-tensioning cable right here in a slab, and we were asked to determine whether there was tension in the cable. And you're basically using a handheld hydraulic pump and a displacement gauge and an A-frame, and you're basically pulling the cable. You're cycling it about three times, and then you're able to determine off of that with the load cell readings. It's a load cell back in here. We can actually figure out within 3 to 10% error as to what the tension actually is in the cable. That becomes handy if you're doing, I don't know how much PT work you're familiar with, but typically the tails are cut off and you don't have much to latch onto. So in the old days, we used to try to actually pull it with hydraulic ram on the end, and the tendons get released, and you actually, you lose the tendon, which is not what you want to do. One of the cons is that you really have to have almost 24 inches of clear space here where you don't have a bar crossing or some kind of interference, and also kind of 1 inch clearance between cables. So, that sometimes does become a problem. You may have to spread cables that are tensioned, which makes it problematic. But there are some limitations to this. Getting close to quarter till, and I think we're getting close, but I want to, I'm not trying to rush through it. But another one is flat jack testing. This is more masonry. This is actually so it's like a hydraulic ram again with these flat jacks, which are basically plates that are inflated or filled with hydraulic fluid. And what we're trying to do is there's single jacks and double jacks, and you can actually figure out the in situ compressive strength or what forces may be in the wall. So like masonry walls in like historic buildings, there's sometimes issues with deterioration or walls actually bowing out and things. And if you want to try to figure out what the stresses are in there, that's one way to do it. The other way is you can figure out deformations. That's what they're doing here. You can actually put a force in and figure out what the deflection of the masonry is. This is actually load testing. Obviously can be very destructive, but obviously, as you can see here, you try to prevent that with putting scaffolding and things like that. This is actually on the top here, top right corner. This is actually a project I was involved in at Lowe's Motor Speedway up in Charlotte. We actually tested a raker beam and actually put about 430,000 pounds of force in it. We actually designed this system here. Originally, we were going to try to, look at adding loads or water, and we just couldn't get enough of it on there, and they're finished suites up top. So one of the things we did is we actually had 3 load points. We used some Dewey Dag bars and actually created this frame. It's not super visible here, but we basically used soil anchors and pulled the structure down. And anyway, there were some existing retrofits if you've ever been out there, and there was concern that those weren't working, and they actually weren't. And we actually put in another supplemental retrofit in there that's not very visible, but anyway, there were concerns about cracks right in here in the intersection here. But one of the things is, as far as these is a super costly, potentially, depending on the scale of them. And also, obviously, there's a chance of damage. And it's just important up front to make sure all the parties agree on sort of the criteria as far as acceptance criteria. When does a test fail or pass? Pretty important, when you're doing this, to do that up front. And you have to, add scaffolding, as you can see here, rent other equipment. So it's not simple, but sometimes that's the only solution to resolve maybe some kind of a question about structural capacity. This is actually water that we use, water tanks to fill. We've used pools and things like that too. So there's various ways of doing this. And ACI 437.2 is actually a very nice guide. There are different load tests. There's the traditional 318 test, and then there's the rapid test, which actually goes through cycles and looking at ductility and things like that. So there are different methods to do that. I think I'm going to scan through these pretty quick. 3D laser scanning. We obviously use surveyors to help us with this. Rapid collection of data. The thing is like pretty large files potentially. We actually worked on a couple projects, with just creating the point cloud. There's just so much data, and then really distilling down the data into something meaningful can become very expensive. So the collection itself isn't super expensive. It is the data reduction, really, that's the problem, or can be a problem. It just takes time to get the information out of it that you want. We had actually looked at some things as far as finishes on concrete, out of plane, out of, conditions, and trying to map that out. And it although we got the data out, it took some time to do it. The other thing is, if there are any kind of obstructions like trees in the way, they're going to obstruct the image reading. So that keep that in mind. This was a project where there was a collapse. We did a laser scan of it just to record it. So this is just like one more way to document a potential failure. You can kind of see the image here in the bottom right of the scan that was done. And so you have actual points. So you can actually, all these images, you actually have points. You can actually take measurements off of it and whatnot. And then obviously nowadays, we use a lot of drones. And I say this is advanced because obviously you have to be a licensed pilot, although I know folks do fly these without having the proper licensing. We usually, check with the FAA and things like that. We have folks that do that to make sure we can fly, especially around this area with military bases and things like that. And airports, you've got to be pretty careful. And we can do scans of facades and roofs and attach IR cameras to these drones. Certainly a variety of uses. Downside certainly being the battery life on some of these, but obviously that's improving a little bit. But you can kind of see these are some of the IR images you can take pretty quickly, get IR images of roofs versus kind of walking it. It may be easier to access things too. It also can help you kind of pinpoint areas maybe that are difficult to access, that whether do you need to get a lift or something or get closer to this. This is actually a project, I don't know if you guys recognize, this is actually in Hickory, the recent arches that collapsed. We're involved in that project. And we're doing 3D imaging of that to help us do our evaluation. So lastly, as Jason kind of mentioned, many NDE inspections and testing techniques are available, but the selection of the appropriate one will be critical really to get the correct answers that you're looking for. So that's kind of one of the things, you definitely want to reach out to folks to get help determining what is actually something that could be useful to you. And when completing NDE work, really one of the things you have to look for is verification of the data. You can't use it like a black box. Doing exploratory openings and things like that is pretty important. Knowing that you're doing the right thing as far as the equipment, as I mentioned before. There are some limitations. Proper calibration of that equipment, that's kind of a maintenance thing that you need to keep up with. Sometimes it's these things too, they have software that needs to be updated and could make a big difference on the results you get. And then, understanding the limits of the equipment, and certainly, understanding also the limits of their operator of that equipment, and that they have the proper experience. So with that, I'll pass it on. I know there were some chat questions. And let me see here if I can scroll through. As far as one of the things I saw, sharing the slides, we can put together kind of a low note thing, and I can get that to someone with your group and get that distributed if you like. That's the same question. It's the same. I guess those are the only questions. I don't know if anybody else wants to, certainly, instead of chat, if they want to ask verbally a question of Jason and I, that'd be great. We appreciate the opportunity to talk to everybody, and would look forward to doing another one in person, hopefully soon.
This is Joe Lorick. Do you do actual material testing in conjunction with your investigation capability?
Yes, sir. Yeah, we actually have a full, lab. It's not in Raleigh, but we have a full materials lab in 3 locations actually. So we can do photography. We actually have a division that does mobile bridges. We have metallurgists. We've got a organic, inorganic chemistry lab, those kind of things. So it really can look at a lot of variations of materials.
Thank you.
Yes, sir. Thanks.
And I'll just make a comment that this is an extremely interesting presentation to me.
Great.
I'm in the construction end of things, and it's a very, very good overview for, figuring out what I need to do in the future when we run into issues.
Thanks. Yeah, thanks for sharing that. And certainly, there are lots of other tools out there, and the technology is just moving at a blazing speed too, right? And one of the things, that is too, is like some of the stuff we're testing it. We actually do some in-house research. We have actually embarked on a new program in the company where we fund our own research to share, with others. And it's kind of one of those things. A lot of our folks are very involved in committees and things like that. The ASTM standards, some of the things that you're seeing there are actually folks from our company that are involved in those. And then actually some of the equipment, some of the testing procedures and things we actually have developed. So, so if you needed some kind of resources like that, we certainly have a lot of folks. Jason and I may not be exactly the guys, but we can certainly help, find the right folks within the company if somebody's looking for that help. And certainly be glad to talk to you about, anything, questions, different questions. And you've got our email addresses here. Feel free to reach out if you think of a different question, even, after this presentation. We'd be glad to talk to you.
Thank you very much, Ralf and Jason.